Hello. This is the third in the discussions for the quantum physics section for the IB, and here we're going to be looking at the idea of atomic spectra and atomic energy states, and we're going to be looking at these. So the first part outline a laboratory procedure for producing and observing atomic spectra. This is a bit of review. And to read up on this, I would suggest that you go to your textbook, and this is page 175 of your textbook, page 175 of your textbook, and this is looking at your emission spectra. And to do that, you have a glass tube evacuated. You can use mercury vapor, and if a high potential difference is applied, there is a glow, there is light. And if the light that comes from this is split into its component wavelengths, then you will see the different line spectra coming out, which shows that. Okay, so this is a way of producing a line spectra. We also have, if we go further down the page, you will see that we can see for absorption spectra. It's at the bottom of the page for absorption spectra. And here basically you get a filament lamp, so that produces a whole range of light. But if it is passed through unexcited mercury vapor, and then afterwards, we will find that afterwards you look at it's focused and you look at the spectrum, it is still continuous, but there are these dark lines, and these dark lines are where the mercury vapor actually absorbs specific wavelengths of light relating to their absorption spectra. So this is a way that it can where you can get this in the laboratory. So I hope you find it useful. It'll be good for you to read that again. So going back to this, now the idea here was explain how atomic spectra provides evidence for the quantization of energy in atoms. This line spectra produces that because only very specific wavelengths and therefore frequencies and therefore energies are emitted or absorbed, and that shows that the energy is indeed quantized. Now we can actually calculate the wavelength of the spectral lines from the energy level differences and vice versa. And just to explain that, I'm going to use the example that is actually given also in your textbook. It's this one over here, and here we have 3 energy levels, and these are the energies. Now, important that you notice firstly that we are dealing with EV, and the formula that we're going to use is E is equal to HF. But this E, if you're using the regular units for your Planck's constant H, is given in joules. So firstly we must make sure that we always convert our EV to joules. So when you go from EV to joules, you always multiply by 1.6 times 10 to the negative 19, which is the charge of an electron, 1.6 times 10 to the 19 coulombs. So in this case over here, for the B, it drops down, so it's going more minus. In other words, it's becoming more stable, so it's giving off energy in the form of a photon as it drops down, and that energy will be related to the difference in the energy levels. So what we would do is that our E for this would be 1.5 minus 0.85, that's your difference in EVs, times 1.6 times 10 to the negative 19, to put that into joules, is equal to Planck's constant, which is H, that's about 6.6 times 10 to the negative 34, times your frequency. So obviously we're going to divide the 6.6 times 10 to the negative 34 here. That will be cancelled there, and we'll get our frequency. And we should be getting a value once you do that on your calculator of about 6. We're looking at B here, 1.6 times 10 to the 14 hertz. So the frequency for B is equal to 1.6 times 10 to the 14 hertz. I can do the same thing for A. Now A is going all the way down here. So there we are going to do the same thing, but instead of having the 1.5, we're going to have the 3.4 minus the 0.85 to give us that difference there. And if you do it, you get your frequency for A of about 6.4 times 10 to the 14 hertz. Well, that's what the textbook says anyway. So looking at that, we see that obviously FA is a higher frequency, and therefore a higher energy light or photon than frequency of B. So this is how you can calculate the frequency. Now obviously for this we can then go to our formula and calculate the wavelength. So I know that my my wavelength is going to equal C over the frequency. So let's just work it out for the frequency B. We're going to have 3 times 10 to the 8, that's the speed of light, divided by 1.6 times 10 to the 14. And if I work that out, it comes to about 190 nanometers, or 190 times 10 to the negative 9 meters. Alright, so it's pretty straightforward, very easy algebra. It shouldn't be any problem for anyone. Thank you very much.